All right, the discharging capacitor. So at this point, we've fully charged the capacitor. So we're starting our analysis out here by assuming the charging process is over. So the battery voltage has fully charged the capacitor. So we're looking at conventional charge, positive on the top. The negative terminal is going to be based on the bottom terminal of the battery being ground voltage. So our capacitor is fully charged. And now we are switching the switch to B. And when we do that, we're creating a current loop here. So put this into your notes. So this is the current loop we are generating. That is our Kirchhoff voltage loop analysis here. So this is the loop. And what's important to know about the discharge of the capacitor is even though we can think of, well, the resistor is stagnant and grounded, it's part of this purple loop. So we will get a current flowing through the resistor as the capacitor discharges based on this purple energy voltage. Some of the voltage sources equal some of the voltage drops analysis. Now, we don't have a voltage source, so what's important about the discharging capacitor is to realize we don't have a voltage source like a battery. So the voltage sources refer to batteries. Even though we can think of the capacitor as a source of the voltage in this problem, as it says here, and please make sure you get this into your notes, both of the voltages are dropping. The voltage across the capacitor is getting smaller. It's dropping. We always speak of Ohm's law as a voltage drop allowing current to flow through the circuit. Now, the trick to solving the differential equation is no different than the trick we used for charging the capacitor, where we replace the current I with dq dt, and Q equals CV, V equals Q on C. So this is our differential equation. So this is the differential equation. That governs the motion of the charged particles as the capacitor discharges. And we do separation of variables. It's kind of all the same, but what's really easy now is there's no U substitution. So we separate the variables, meaning the dq and the dt. We again let our limits of integration go to any time t that is in between fully charged and no charge. So we don't go to the full endpoints because we want to generate an equation. So this little t is between fully charged and no charge, fully discharged. And we go from capital Q, fully charged, to any little q that is between fully charged and no charged. And we can see that we get a 1 on q dq, natural log of q, final minus initial, natural log of little q minus natural log of capital Q. So natural log of A minus natural log of B is natural log of A on B, and we are done. So we are going to let natural log is base E, let E operate on both sides, and just as we got our equation for Q as a function of T for the charging of the capacitor, we want to memorize that the charge as a function of time on a capacitor as it discharges is going to be based on the total charge on the capacitor that it's going to discharge, falling off exponentially according to e to the minus t on RC. So the nice thing is that all the graphs we're going to see are going to be the same in that the charge on the capacitor falls off exponentially. So this is an e to the minus t on RC drop. This is going to be an e to the minus t on RC drop, and this one is going to be an e to the minus t on RC drop. So Exponential decay. We know that the voltage across the capacitor always follows the charge on the capacitor. So those concepts, our initial understanding of capacitors has not changed throughout any of our analysis. So the Q equals CV. So we go from here to here. If you want to put it in, then V equals Q on C. So that gives us our voltage across the capacitor. This will be our maximum voltage that we started with. It drops, and again, it drops off exponentially. And finally, we can calculate the voltage drop across the resistor by taking the derivative dq dt. So if we take our Q equation and we take the derivative of it, so take the derivative dq dt, we get the voltage across the capacitor is given by Q, it's e to the u du, so e to the u, this is du. So when you take the derivative, I can squeeze it in up here. So when we take du of e to the u, remember your derivative of exponentials, it's e to the u du. So the -1 on RC is the du that we get, and that's where we get the voltage drop. The negative would indicate it's a voltage drop. So the absolute value is what we're looking at here. Q on C, the maximum voltage on the voltage drop across the resistor happens immediately, and then it drops off exponentially. So much easier analysis than the charging of the capacitor. It's still helpful to go through. And we can discuss this in class if you have any questions.